Welcome back to part 3 on trigonometric equations. We're going to use your graphing calculator to find the solutions correct to 2 decimal places for these given examples. So let's start off with cosine of x equals x divided by 5. We can think of these as 2 different equations set equal to each other. So if you think of cosine as being this function here where it just continues on, and we think of x over 5 as being this kind of shallow, linear graph, something like this. We need to figure out how many times the 2 equations will hit each other. And it's helpful if we can just kind of sketch a graph like this first so we know what to expect. So when we put it in our calculator, we're not surprised by what we get. And then we just look for the intersection coordinate points, which I don't know until I actually graph it. So let's do that next. In my y equals, I'll put x divided by 5 and cosine of x. And I'll just double check my window here. Let's make this be in some sort of measurement that makes a little more sense. I want to go from negative 2 pi to positive 2 pi. And in the y direction, I want to go from, let's say, negative 2 to 2 and see what happens. There's my linear function, and there is my cosine function. Now I can see that it is crossing, the cosine function is crossing the x over 5 function in 1, 2, 3 places. 1, here, 2, and 3. So let's go ahead and find the intersections. Second, calc intersect. And we're going to go through a process. So it's asking me to identify the first curve. So I'll go ahead and say, yes, that's my first curve. Now it's hopped to the other one, and you say, yep, that's my second curve. And now I need to guess an intersection. And so I need to arrow to the left because I want to start with the smallest x value. So I'm going to guess that intersection point. And the intersection is at negative 3.837. So I'm just going to go to negative 3.8. And in the y direction, I'm at negative 0.77. The first solution to the 2 is at negative 3.84, comma, negative 0.77. Now let's check the next one. Go through the process again, second calc intersect. Say, yes, this is my first curve, enter. This is my second curve, enter. And then guess the next intersection point. The next intersection point is at negative 2, if we round, negative 2.00, and negative 3.95, so negative 0.40. And I'm going to go ahead and sketch this just a little bit further out. So this first point here is that point there. The next point we have is negative 2.00, comma, negative 4.40. And then the last one, second calc intersect, will be right here. So we need to give our lines. First line, yes, enter. Second line, yes, enter. And then arrow as far over as we can until we get to that last intersection on the right. Hit enter. And we have our last intersection at 1.31 and 0.26. So I hope that helps figuring out how to do this. It's not incredibly intuitive, but if you think of these two equations as being separate and then being set equal to each other, it's saying, hey, where are these two functions equal? Where do they intersect? Now we also have this next example where we have sine of x equals x cubed. I'll go ahead and graph the sine function here. And then I'll graph the x cubed function. X cubed kind of looks like this, where it kind of kinks at 0 and it approaches negative infinity in the y direction as x approaches negative infinity, and it approaches positive infinity as x approaches positive infinity on the right in the first quadrant. And so you would assume that these values would be in some way symmetric where they cross. Clearly they're going to cross at 0, 0, but then we also need to look at where they would cross up here. So we would go through the same exact process with the calculator for this example, and you should get 0.93, comma, 0.80 in the top right quadrant, and then a very similar output in the bottom left quadrant, the third quadrant. That will be negative 0.93, comma, negative 0.80. Next, we need to find all solutions of these equations. So we're going to just have to factor these if we can, and if not, we'll have to just solve for the angle theta. This first example gives us 2 tangent of theta plus 1 equals 0. I'll go ahead and check for degree 2, which it doesn't have. So the next thing I'll do is isolate the trig function on one side. That gives me 2 tangent of theta equals negative 1 by bringing that 1 over. Then I'll divide both sides by 2. And that gives me tangent of theta is equal to negative 1/2. Remember that one period for tangent is between negative pi over 2 and pi over 2. We're looking for where this function equals negative 1/2. So here's my sketch, y equals negative 1/2. And I've sketched that along horizontally below the x-axis, and I'm looking for that intersection point. I'll go ahead and show you how you could put this in your calculator. First, I would take y equals -1/2 as one of my entries. And the next one would be tangent of x. We know it's theta in this case, but my variable is x. And then I'll graph this. And I'm looking for this intersection right there. It's in the third quadrant. It's in the third quadrant. So I'll just do second calc intersect. It's checking which curves I'm looking at, and I'm saying yes to both of them. And then I'm going to guess the intersection location, which is about there. And it's telling me that my intersection is -0.46, comma, -1/2. If you were to think about the fact that this curve for tangent just keeps on going to the left and to the right for these intervals of pi in length, we could expect that every one of these repetitions for tangent would have an intersection just like the previous one. So you need to think about how you would find all the solutions to this equation. Well, I know that if I add pi to my already given -0.46 in the x direction, I would get to the next intersection point. And then if I added another pi, I would get to the next intersection point. So I could say that theta is equal to -0.46 plus pi k. You'll see pi k. You'll also see another way you could write this is -0.46 plus n pi. It's kind of up to you. Again, the notation, you have to keep track of how your homework wants you to notate this stuff. But either one of these makes sense. You're just assuming that n or k is an integer, and that's how you're adding to get to, you're hopping from one intersection to the next intersection to the next intersection. Now this last one here, we have sine squared theta minus sine theta minus 2 equals 0. So we're going to use factoring and the zero factor theorem, which just means you're setting your factors equal to 0 and solving for theta. So I'm going to factor this. I have a sine theta and a sine theta, which gives me the sine squared theta if I were to FOIL it. I need a difference of -1, so my 2 is going to be negative and my 1 will be positive. If I set my factors equal to 0, I'll have sine theta minus 2 equals 0 and sine theta plus 1 equals 0. And then I'll solve for sine theta. Sine theta is equal to 2, and also sine theta is equal to -1. Recall that sine of theta cannot equal 2, so we will throw out this one because it's not possible. Because recall that sine inverse of 2 in your calculator, let's see, does my calculator explode? Second sine inverse of 2 gives me a domain error. You can either go to the error and look at what it's telling you. It's saying 2 is wrong, but if you didn't notice that, hopefully you recall your rules for the domain and range for inverse functions. And then the next one is sine of theta equals -1. Now this one's more reasonable. or sine of 3 pi over 2 will give me a negative 1 in the y direction on my unit circle. You could also have done theta is equal to sine inverse of negative 1. Hopefully you have your unit circle memorized so you know that it's just 3 pi over 2. And then we just need to think about, if we're looking at the sine function and it's repeating, when does it equal negative 1? And I would say that that happens every 2 pi, which means that I can say that my solution theta is equal to 3 pi over 2 plus 2 pi k, and assuming that k is an element of the integers.